Record is rolling. It is Friday, September 19th. You guys have your laptops open, ready to go. I'm gonna have you guys download some Paul Hewitt videos, show you guys where those are. Okay. So on Google Classroom, you guys go into Google Classroom. Okay, okay, today's September 19th. I'll upload today's video here later, but this VT video isn't. All right, so that's it. But if we go scroll way back, way back, way back to the very first week of school, actually even before that, Billy. Go view more, keep scrolling down. You guys see Paul Hewitt demos right here? All right, there's two zip folders. So if you right click and open in a new tab, then there should be like a down arrow. You'll be able to download these. No, some of my students were able to do this earlier, and some the internet didn't allow. Oh yeah, okay. Okay, I'll have to get that to you later then. Okay. All right. So,
Yeah.
okay. Here, let me see if it's like right here. You can join real fast. Here, real fast. All right, it's PVI 7 SHSO. There, it's on the board now. All right, so gonna walk around and troubleshoot, help you guys out here. And in the meantime, I got something's gonna tie into what we're gonna do today.
Let's show, by the way, it's Apple. And these as well. These are sharp nails, gang. Okay? About an inch apart. If you don't know what an inch is, think about 2.54 centimeters. About 2.54 centimeters apart, all right? And Paul is going to. You sure these are Teflon coated? No, these are the real thing, honey. You know why we don't do it the other way around? That's a good question. This really is dangerous. And Paul's a little more foolish than I is. No. Paul, get more area. Thank you, no. Okay. You're back, Robinson. Oh, a day's work. Yeah. It's for science. Have to have Red Sox. Okay, you guys protect yourself. Protect yourself. Yeah. Okay. Okay. Here we go, gang. Here we go. All right. 1, 2. I should tell you. This is not mind over matter. It's not what kind of granola or bean sprouts or meditation that Paul does. You know what this is all about, gang? Physics. Yeah. Okay, let's see it. Here we go. 1, 2, 3.
Ooh, all right. So there, there. Hold on to the idea because that's really the something we're about to be doing. Right. Here, let me show you guys two. Right. So I'm on Brevard Launchpad. If I go to Savas, SAVVAS, I think you guys have a similar icon. Getting access to your book here. I was trying to show you a few weeks back, and it was kind of right. But are you kidding me? What? No, 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 no. I did try this earlier, and it was working. Come on. Okay. I was just using this earlier. Let me try one more shot here. Boom, boom. Come on. Okay. Okay. Let me in there randomly, guys. Okay. So I think from your side, it should look similar. It might look tiny. Experience physics. I click on that. Okay, and then it'll bring up your book. Okay. Boom, boom. Your Okay. All right. And then here's your book. All right. You see the cover right there. Okay. Click on that. Okay. So you guys have a digital version of your book. All right. All right. And then, yeah, it'll bring it up here. All right. So I can go to ebook right here up in the corner. Experience physics, student book. All right. Student handbook. All right. All right. And then you can navigate through the table of contents. All right. So every physics textbook is organized a little bit differently. Your book doesn't say chapters. I think it says like experiences or something like that. Something like that. Um, or storylines, investigations. Okay, there it is. So storyline one, forces in motion, which is a lot to push in one chapter, but regardless. Okay. Okay. Anyway, this is really slow loading, but you can get your book this way, and you can like flip the pages. Right. So you guys see sort of how to access that. It's through Savas. Right, here we go. You can like click on one of these, go through these storylines, and then flip the page there. Okay. So just show you guys how to navigate through your book there. Okay, close that off. Let's go back over here then. Okay. All right, so you guys downloaded the zip, or some of you guys were able to, and if you weren't, you can try this at home. You can unzip it, and there's a bunch of Paul Hewitt videos there, a lot like the one I just played for you guys. It's gonna tie into what we're doing today. All right, so we're gonna, okay, I just played you guys this one. It's gonna tie into how this works. So we're gonna go back and debrief this, and then my goal after that is to go through three puzzles with you guys. So I want to do this puzzle with you guys today. Right now, today's gonna be a little bit of a challenge, but plant some ideas going into the weekend. Right, I want to do the car braking to a stop with you guys today. Okay, and then I hope I have about 3 minutes left over at the end of class that I can at least set up a block on an incline with you guys. I show you guys how to think about this type of thing. So categories questions. All right. So we do this. That'll bring us to the weekend. And this weekend, yeah. Again, I don't have any due dates on any of the assignments yet, but here's maybe some things that you could jot down some things in your notes. You guys know the more time you spend on any subject or anything, you only set you up and you can get better at these things. Right? So since you guys just downloaded Paul Hewitt, or you know how to do that, you can do Paul Hewitt Watch Party. That sounds fun. No, chapter 4 or 5 is actually for a different textbook, but I showed you guys how to access your book. Right, so I think I call it Investigation 1, something like that. You could, I just handed you guys your textbook puzzles, or the ones I copied out of the book that I thought looked interesting. And so you could at least read the question. You might be able to solve some of these, maybe. Right? Maybe not all of them, maybe some of them. Don't worry about AP stuff. You could review your notes. Right? You guys have a bunch of free body diagrams from yesterday and maybe notes from before. And we're going to do some notes today, or take you guys through these examples if I can. Okay. And then, quiz corrections. So you guys got your quizzes back. You guys know if you missed any question on a separate page of paper, you can write out how to get to the answer, or if you missed a graph, draw the correct graph, save your quiz to that, turn it in, and that will give you partial credit back. Okay. You can rewatch any, say your favorite Google Classroom video. Make one right now. I'll post this to Classroom later. All right, so that is our agenda. All right, you guys go down the agenda. What you guys are doing over the weekend? You guys got planners? Do something. Okay. All right, so how does this cup work? So reminder of the premise here. Okay, so I have this cup. Here's like a cross section. Okay. I filled up this cup halfway with water, and the water stayed in the cup. Then I filled it up to the brim with water, and it was raining out. But in fact, the entire cup drained. It's just like little tiny water. Okay. So the question is like, how is the straw connected? I see some kind of straw hole there. I see some kind of straw hole here. Okay. How does the straw connect on the inside? Okay, so who's got this figured out last couple days? Anybody figure this out? Got an idea?
Straw like curve to the left or right.
Aha, it has to curve, right? Okay, something about the straw curving is definitely not a straight shot. Okay? In fact, guys, if I fill it halfway and it does one thing, and I fill it to the brim and there's a total state change. Huh. Who thinks the straw has to, yeah, what do you think?
It's tension and the more weight it breaks through, and then it just like I forgot the word, but it like leaves all of it out.
Yeah. How do you guys think the straw has to like come up here? Like come all the way up here? Probably? Something like that? Right. Actually, I have a poster for that. Right, it goes like this. Here's the answer. It's called a Pythagoras cup. If you wanted to Google it, right, you Google Pythagoras cup. Right? Yeah, so the straw goes up the side. Right? So if you fill it up halfway, yeah, there's some water that goes in the straw, but it's just going to stop right there. Right? But if you fill it to the brim, it floods the straw. Okay, so it starts leaking out the bottom, so draining out the bottom. Okay? And then at some point, the water level reaches the original water level. Right? So it's like back down to where it was. But this picture on the right is still different than how it started, because now the whole straw is flooded and the rest of the water gets siphoned out. Right? So water wants to reach the lowest point. This is the lowest point down here. Right? And even if it has to go uphill to get there, it can siphon through. It can siphon out, and the whole cup drains. That's it right there. Okay? If you look under your sink or you look back behind the toilet, you'll see that same type motion, that siphoning type motion right there. Okay. Now, how does that connect to that bed of nails? I played you guys that Paul Hewitt video with bed of nails. Because what physics variable was he talking about with the bed of nails? How about pressure? Yeah, pressure, right? Right. Because isn't pressure like force per unit area in physics? The unit could be Newton per square meter, right? Guys, would you rather lie on a bed with one nail or a bed with 1,000 nails? Yeah, let's go with 1,000 nails. Because your weight, which could be quantified in newtons, is now distributed over 1,000 times the tiny cross-sectional area of a nail. So if you have 1,000 times the area, that'd be 1,000th of the pressure, wouldn't it? Yes, that's how I bet a nails, right? And how does that tie into this Pythagoras stuff? Well, because we're in an atmosphere. Are we in an atmosphere of like 100,000 of these pascals? Right. Like, so here's 1 Newton of weight, right? And 1 square meter, you guys imagine this big old foam board of 1 square meter. So 1 Newton on 1 square meter would be 1 Pascal. Aren't we sitting in 101,000 of those right now? Right. Also called 14.7 pounds per square inch. You have a 14.7 pound bowling ball on every square inch of you right now, right? Right. So that's what this cup is in. It's in an atmosphere. Would this work in a vacuum? If I took this to the moon and I fill it with some liquid, right? Would this actually drain? Would it siphon out all the liquid?
No.
Yeah, it would not. It would not. Right? Because by the time we got to like this snapshot right here, what happened in a vacuum is that this liquid would split. It wouldn't even be contiguous anymore. Right? And then it would just kind of stop right there and it wouldn't siphon out. Right? But guys, the fact that we're inside of a pressurized atmosphere, there, yeah, it keeps this liquid contiguous, right? And the whole thing's able to siphon, right? But that only works up to a point, right? There's only so tall I can make this cup. Right? So let's start thinking about that. Let's think about atmospheric pressure in a different way. Suppose you were in a pool. You guys ever go swimming in a pool? You guys go to the deep end and dive all the way down to the bottom? So now, can you guys feel the pressure going up?
Yep.
Right. How deep would you have to go so you effectively double the pressure on you? Like here, we're sitting in 1 atmosphere. As you go down, feel the pressure increasing. How far down to get to 2 atmospheres? How many meters? What do you think? It's about 10.3, about 10.3 meters, right? Which is about the width of this room, by the way. You turn it sideways, fills with water, dive down. Yeah, about 10.3 meters, right? Actually, what that another way to contextualize that is right now how it feels compared to the vacuum of space. It's sort of as if we're at the bottom of a 10.3 meter swimming pool full of water, right? It's the same pressure, right? Which means that suppose you put a straw in this water, you start like drawing water, right? What if you had a really long straw? Because what's the longest straw you could theoretically use and it would still draw water? 10.3 meters. Yeah, the equivalent to atmospheric pressure, right? Because straws work on a pressure difference. People figured that out back in the day. There was some lake down here. Could this be a lake? And this could be like a hill, and there's a town sitting on top of the hill. You guys see that? Right? They said, hey, let's start pumping up the water from the lake way down there. Oh, that's a great idea. So some of the first pumps a few hundred years ago. Right? But then they realized after about, you got different towns and different lakes and different heights. They could only pump up to about 10 point something meters, and then it would run out of pressure, and they couldn't pump up all the way. Ooh. Maybe they have to do like a halfway and then like pump it up after that. Right? But how about guys? What's the tallest Pythagoras cup I could make and it would still siphon all the water out? 10.3 meters. Right? Once it's beyond that, it doesn't work anymore. Right, so there you go. There's a little pressure. All right. So all right, you guys ready for next puzzle? Next puzzle is this one right here. It's right here. All right, so I'm gonna stretch your guys' imaginations a little bit. All right, so you guys ready to turn your brains for the last half hour of school and do a little algebra right here. Right, so the premise is going to be this: I'll give you a weight, and I'll give you a couple of strings at some angles, and I want to know what's the tension in each string. Right, you guys ready to do that? Right, you guys got your notes out. So, where's my ruler here? Okay. So, put a dot somewhere, like center left on your paper, somewhere about there, okay. And let's have a weight going straight down. Now, I could call the weight F sub G, okay, or mass times gravity field mg. Okay, and I'll give you guys a number. Let's call it an even 100 newtons. Okay, keep it pretty basic. 100 newtons. 100 newtons force. Okay. And then I'll have one string tension going, let's say pulling kind of up and to the right. Let's have this one fairly horizontal-ish, up and to the right. And I'll have one string tension pulling up and to the left, but that'll make this one more vertical-ish. More vertical-ish. What's that? Okay. There's a reason that I drew those arrow vectors, those corresponding relative magnitudes. Like this one's short, this one's a little longer, right? So in your notes, do your best to probably pretty close to what I have, and then this will look really nice visually. Okay. I need to label these. Let's call this tension on the left side and tension on the right side. So T sub L and T sub R. That's okay, right? Okay. So T for tension today. Okay. Now, with the exact tensions, it has something to do with this 100 newtons, but doesn't it also have something to do with the angles they're at? If I change the angles, maybe the tensions would change. Okay. So I do have to give you some angles. And for that, I have to say the angle with respect to what? So we're going to introduce a Cartesian system. Let's have a y-axis running straight vertical, say parallel to gravity, which conveniently the weight is already aligned with that axis. Right? So that's good. It's like sort of my y-axis. Right? And then perpendicular to that, I'm going to run off an x-axis. Right? So you guys also in your notes have an x-axis and a y-axis. I said that. Okay. So you cannot solve this numerically unless I give you the angles. So I'll give you an alpha right here. Let's call this 30 degrees. 30 degrees is a really common angle, so that one's good to know. And this one right here, I'll call beta, and I'm just going to make up something. How about 71 degrees? Just something crazy. Okay. So I don't know. We'll see how this plays out. Okay. Now, to make sense of this and be able to solve this, remember, these tensions are off on diagonals. I have to put them in context of that Cartesian system. So doesn't this up to the right tension pull kind of up, kind of to the right? So I'm going to dash, 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 dash. Notice I'm breaking the tension into components. And same thing on the other tension. So this other tension pulls kind of to the left and kind of up. So I'm going to dash these, dash, dash, dash into components. The fact that I'm dashing them means I'm not double counting them, sort of like the solid vectors or the actual vectors. There's only three forces on this point where all the strings come together. Okay? But then taking the diagonals and breaking them into components, and I'll solve all the algebra in terms of those components. Right? You guys get that concept? Right? That concept? Okay. Let's do some sine and cosine. Figure out what are these values. Again, I don't know the tensions yet. That's the question. Okay. But in terms of the angles, could I say, here, let's start with, how about this one right here? This could be the tension on the right side, whatever it is, times what? Sine or cosine? Cosine of 30 degrees. Aha. Do you guys see that? Cosine 30 degrees? Okay. Could I continue to do that for the other three components? Yeah, I'll do that right here. All right, so this bit right here, be tension right times sine of 30 degrees. Okay. This component here is tension left times cosine of 71 degrees, and that's to the left, so I'll keep that in mind. And then this bit here would be tension left times sine of 71 degrees. All right, so I got my components, or at least I'm a step closer to figure out what they would be in terms of the total tension. All right, is it? Okay. But you know what? Sine and cosine of some particular angles. Couldn't I pop that into the calculator and figure out like the exact decimals? Right? So, some decimal between 0 and 1. Okay. Like, how about sine of 30 degrees? Yeah, I'll start with that. Okay, sine of 30 degrees, I think, is a good one you should know. Does anybody know what is sine of 30 degrees? 0.5! Ah! Winner! 0.5 exactly. Is exactly 1/2. Okay, exactly 1/2. Okay. So what that means is that this component, I'll say equals, is exactly 1/2 of the full tension on the right side. 1/2 of TR. Here, I'll go ahead and circle that. Okay. So we'll come back to that later. All right, and then if I replace, huh?
It's hard to see glasses.
Huh? Yeah. Okay. Okay. Okay, so we got tension on the right times sine 30 degrees. Sine 30 degrees is half. So that would be half of the tension on the right side. Okay, so 1/2 of TR. 1/2 of TR. Okay. Okay. If I replace sine with cosine, I'm getting this one down here. This is 0.8660. So this is 0.8660 times tension on the right side. Okay. So that's another component. Right? So sine and cosine. Right, same thing on the left side. Now this angle's different, so I'll change to 71 degrees. That's 0.3256. So 0.3256 times tension on the left. All right, circle that one. Okay. And then if I do sine, oops, sine This is 0.9455. So this is 0.9455 times tension on the left side. Okay. Boom, just like that. Okay. So there's my four components. I circled those, like the decimal height values. Okay. And then I do have this 100 newtons pulling straight down, so I'll circle that one too. So I circled 5 values, and that's going to feed into a couple of equations. Okay. Got it? Okay. Next step. So the guiding framework here to solve this is, well, these two conditions here. So for equilibrium, the sum of the forces goes to 0 newtons. In fact, if you have a Cartesian system, that's also true along each axis. So the horizontal and the vertical, that's still true. So here's my conditions. The sum of the forces in the x direction goes to 0 newtons, and the sum of the forces in the y direction also goes to 0 newtons. Okay? So that's my system condition. Okay? So I'm going to set up an equation for each one of those conditions. So in the x direction, bring this down here. In the x direction, isn't it just these two horizontals that zero out? In fact, you can see why I drew the picture the way I drew it, where I made the right tension kind of short and the left tension kind of long. I set it up for this very reason. You guys see these two horizontals pretty well cancel out? And ideally, they should. Like if in your notes they exactly cancel out, then you drew like a perfect picture. Right, so I got here. This would be 0.3256 tension left. Oh, I should have done negative. No, that's all right. Here, guys, kind of stop a negative because it's pulling to the left. Is that okay? Okay, negative is left. Okay, and then plus 0.8660 tension right. Okay, that sums to 0. That would be newtons. Okay, instead of negative right here. And then in the vertical, I'll set up a different equation. So the vertical, I see 2 upper components, and then the weight pulls down. So now I'm juggling sort of like 3 terms, right? So I have this one right here, which is 0.9455 tension left. Software, right? Plus, well, okay, 1/2 if I like tension right. And then minus 100 newtons goes to 0 newtons. So that's my system right there with values plugged in. Okay, so here, pause point, give you guys a recap, bring you up to speed while you're digesting this. Right? So there are 3 proper forces. My weight is already aligned with the Cartesian system, shows up here, by the way, in the equation. And then the diagonal tensions, I don't know what they are, I still don't know what they are. Right? But I do know the angles. So in terms of sine and cosine, it can break them into components and set up a horizontal equation and a vertical equation. So horizontally, there's just these two cancel out, right, left. This one pulls right, this one pulls left. So this is positive, this one's negative, there's a little negative there, and that zeroes out. Okay. Vertically, there's 3 things going on. There's these 2 components pulling up there, and there's the weight pulling down right there, and that also zeroes out. Sure. So I have 2 independent equations and 2 unknown values, which is each tension left and tension right. Guys, can you solve an equation with 2? Can you solve a system of equations, 2 equations, 2 unknowns? Yep, that's definitely solvable. Right? Definitely. Right. So let's do some substitution. All right, substitution. By the way, you could also do elimination. It's a little bit different for that. But well, from here on out. All right, you guys ready for substitution? Okay. So this paper is getting kind of crowded, so I'll start over here. So I'll start with that horizontal. I'll even label it horizontal. So I have, I'm going to just swap these 2 while I'm at it. So 0.8660 tension right for solid form. Okay. This is minus right here. Minus 0.3256 tension left. Right, is 0. Right. So what I'm going to do is solve for one of these in terms of the other one, and then substitute that into the vertical type equation. Right. So I can add this over. 0.866 TR is equal to positive 0.3256 TL. Okay. And then can I divide both sides by this coefficient? 0.866. 0.866. Again, the right tension is, right, what's 3256 over 8660? zero there, is 0.37598. That rounds to 3760 tension left. Okay. Okay. So I'm gonna hold on to that because that's an important middle step right there. Okay. Now I still don't know what each individual tension is. What I do know is that the right tension is about 37% of the left tension. Aha. Okay. And that pretty well aligns with my picture too. You guys see how the right tension is way shorter than the left tension? If my picture is exactly to scale, this should be about 37% of this. Aha. You see it? Yeah, it fits. Okay. Okay. So let's go back over to the vertical equation. Vertical. Okay. And that's this one right here. So I'll say 0.9455 tension left, right, plus 1/2 tension right. Can I just slide this over, say it equals 100 newtons? Like that would also be true, right? Just slide that over. Okay, so that right there. You guys good? Okay, now I know this tension right here. I can just substitute that right there. Substitute in terms of tension left. And I'm about to get one equation with one unknown. Ah, we're getting close. So this tension left plus 1/2 of 0.3760 also tension left. Woo! That comes out to 100 newtons. So put this all together. So what's 0.9455 plus half of 0.3760? This is 1.1335 tension left is 100 newtons. Okay, all right. And then, can I divide both sides by this coefficient? 1.13. 1.13. Okay. 100 divided by the answer. Okay. I'm getting tension left is 88.2 newtons. 88.2 newtons. Oh, yeah. 88.2. Okay. And then, once I have the left tension, can I very simply substitute right there and get the right tension? Right? Because we figured that out a few minutes ago. We said, well, whatever the left tension is, the right tension is 37% of that. Right? So then times 0.3767, that gives me 33.2, it rounds to newtons. Right? Okay. All right. Okay. It's a lot of little steps. But again, the overall guiding framework here is that if you break these diagonal forces into components, then horizontally everything zeroes out, vertically everything zeroes out, and everything after that is just a page full of algebra. Okay? This looks about right? Because could you guys imagine if there's a 100 Newton weight pulling down? And look at my picture, look at these to scale. It looks like this is like 88 newtons, which is holding like most of the weight itself. But then this tension rise also pitching in with 33 newtons off on a diagonal. Yeah, that looks about right. Aha. Okay, so here I'm going to move on here. You guys know I'm recording this, so I'll post the video later if you need to go back and check that. But while we're still in class, I definitely want to fit this car question in. Okay, so car question: car brakes to a stop. Car brakes to a stop. So how much road? Here's the question. Okay, how much road for the car to brake to a stop? Right? Like what's the braking distance? Right? And so I'll draw a picture here. Okay, got a car, vroom vroom. Okay. I'll give us like an initial velocity of let's say 22 meters per second. Just make something up. Okay. And let's make a free body diagram on this car. Or actually, but before that, I need to give you guys some values. So say given. Okay, so I'll give you some values here. Let's say the mass of the car is like 1,000 kilograms. I'll give you guys gravity field is 10 meters per second squared. That'll be important. Okay. I'll give you the initial speed of the car. Well, I have it right here. I called it 22 meters per second. Okay. Now there is one more thing you have to know. Okay. And would you have to know something about between the tires and the road? What's the coefficient of friction? Okay. So I'll call that mu. Now it could be static friction with anti-lock braking, or maybe you locked his brakes and he's skidding. Or, either way, we'll just do a general view. How about point 5? I'll go 0.5. Okay, and we'll see what that is. Okay, very good. Maybe it just rained. That would be reasonable for if you have a wet road. Let's make a free body diagram. FBD. I'll put that in pinky. Guys, what's one force acting on this car? Yeah, gravitational force. It's weight. So I'll call it mg or F sub g. Actually, you can get it right here. Guys, what's 1,000 times 10? 10,000. That would be newtons. So 10,000 newtons of weight. Well, what's the force from the road holding up the car? The normal force. And is that also 10,000 newtons? Yeah, for this basic case, if it's just a flat road, right? Because the car's not accelerating up or down. These two verticals have to zero out. Okay. Now let's talk about friction. Because friction force could be coefficient of friction times normal force. Okay. Okay. And either maximum static or just kinetic. Okay. And in this case, the friction force, does that point backwards as the car's moving forwards? Okay. And if I draw everything exactly to scale, how would I do that? And I can know how to draw it to scale according to its coefficient. Basically, coefficient of friction is 0.5. Okay? What that means is that the friction force is half of the normal force. So if on your paper this is like 2 inches tall, this would be 1 inch to the left. Because half, or 0.5 is half, isn't it? Okay. So that's this friction force right here. Yeah, I should give myself a little more room. That's good. So it's 0.5 times 10,000 newtons. Wouldn't that be like 5,000 newtons? Okay. So guys, this friction force is 5,000 newtons. You guys got that? Okay. So I'm keep the kind of a quick pace to beat the bell here. But if you want to know something about how it's road to come to stop, we have to figure out the rate the car is slowing down. And that's Newton's second law. Newton's second law of motion, which goes like this. The acceleration is the net force divided by the mass. Right? Now, there are 3 forces on the car, but you guys see that 2 of them cancel out? And the only one left on the board is the friction. So could you guys say that the net force is the friction force? Yeah. Which, by the way, is 5,000 newtons to the left, so I'll actually call it negative 5,000 newtons. Okay? And that's acting on the mass of the car, which itself is 1,000 kilograms. You guys see the acceleration is going to be negative 5, and then Newton over kilograms is the same thing as meters per second squared. You guys see that? Okay. That's the rate the car's allowed to slow down. Okay? Is it just? Okay. Which, by the way, was here the whole time. Isn't that the same for your body diagram? Here's the answer in terms of variables. Let's see, acceleration should be, okay, got a negative to slow down. And then coefficient of friction times gravity. What's 0.5 times 10? Oh yeah! It's 5 meters per second squared. What's that? So going in for the finish here. How much, what's the braking distance? Guys, that sounds like a what kind of question? Is that kinematic? Kinematic? Okay. So here, we're doing this bridge variable. So we solved Newton's second law. We solved for acceleration. We're going over this bridge. And if you want braking distance, well, it's going to be his third kinematic equation. Okay. If I had more time, I would probably try to tease that out of you guys. But let's go. Final velocity squared equals initial velocity squared plus 2ax. Okay. Like nobody brought a stopwatch. I never told you how much time. That's another hint that you need this third kinematic expression. We're going to 0 meters per second. Isn't that a full stop? 0 meters per second? Yeah. We started from 22 meters per second. And don't forget to square that. And then this acceleration, we came up with negative 5 meters per second squared. And then for some corresponding braking distance. Okay? Okay. So 22 squared, I think that's what, 484? Subtract that over. Negative 484 meters per second squared equals, that's negative 10 meters per second squared x. Okay, so, actually divide by 10, right? Negative 10. So it looks like 48 meters. 48.4 meters. Yeah, guys, could that be about half a football field? Right? So 22 meters per second, by the way, is almost, or it's pretty close to 50 miles an hour, which is like US 1 speed. So if you're on US 1 in a rainstorm and you brake, it takes you about half a football field to come to a stop. That's what that means. Right, you guys got that? Okay. Right, so last thing is, well, here. I do want to have you guys reconstruct this. So I'll go kind of fast. But this takes some practice, and I just want to plant this and help you guys build your motor skills before you take off for the weekend. All right, so block at rest on incline. Okay, so I'll do this a little faster than I like to, but gotta get this practice in right here. Okay, so draw an incline, draw a block on the incline, okay, draw a center mouse dot, and we're gonna label all the forces. And there's a particular way we go about this. Okay, so I think this block has some weight, because if it didn't, if it didn't have any weight, then it would just be floating around, nothing else inside going on. Okay. Now, everything else here on out, we're going to introduce a Cartesian system that runs parallel and perpendicular to the surface. Notice I'm dashing off parallel, perpendicular, not to the floor, not to gravity, but to the surface of that incline. It's those dash lines. I'm going to break this weight force into components. Say that weight is partially pushing the block into the incline, and it's partially pulling along. Guys, suppose this angle is 29 degrees. Would this angle also be 29 degrees? It's the same angle. So I could call this mg, what, cosine theta? And call this one right here mg sine theta. Okay. So I re-represented the weight in terms of its components, in terms of this rotated Cartesian system. Guys, what's the force that holds the block up from the surface? It's called the what force? Normal. Do you draw the normal force straight up, or do you draw it perpendicular to the surface? Perpendicular to the surface. That's right. That's what normal means. It's perpendicular. Is it equal in magnitude to mg cosine theta? Can you guys see that? Because block's not accelerating in or out of the surface. Okay. I need one more force to put it at rest. Guys, what else do I need? The friction. This friction holds the block in check this way. Friction force. And if the block's at rest, is that also equivalent to mg sine? Okay. So mg sine theta. Ooh, okay, so we got that in just in time right there. Okay, so again, a little faster than I like to, but
Did you record that?
got it. Yeah, guys, this is recording right now. I'm about to close down this recording, and I will post this to Google Classroom. Oh yeah, and you guys have a good weekend.